today in my open school, I'm going to be talking about the cardinalities of countable and uncountable sets. Right now, I'm just going to briefly go over through what sets actually are. So you guys probably saw sets a lot of times in competition math, like probably AMCs and AIMEs. They have a lot of questions that talk about sets, but they don't really go into the details. So the formal definition of a set is a collection of elements, basically. And probably set number A you see over here is probably one of the sets that you see often in those competition problems. So set A is a collection of the elements 2, 3, 7, and 8. Really simple. But now you go to set B and C, it gets a bit complicated. So if you look at set B, it says X is an element of Z, and Z, by the way, is the set of integers. And the absolute value of X less than or equal to 3. What this means is that we follow this rule. The absolute value of X is less than or equal to 3, and that X follows the form of being included in the set of integers. So basically, what are the integers that have the absolute value less than 3? It's -3, -2, -1, 0, 1, 2, 3. And you go to set C. It says the form is 2n, and the rule is that n is a element of B. We established B over here to be -3, -2, blah, 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 until 3. So all we need to just do is for each element in set C, we multiply 2 to the corresponding elements. So set C is going to be -6, -4, -2, 0, 2, 4, 6. And one property of the sets is its cardinality. So if we read the definition, the cardinality of set A is a number of elements it contains written as the absolute value of A. So obviously absolute values, as we know, represents like in a point, it's like a distance between the origin, and it's basically like the magnitude of its value. And it's similarly used in sets. So in set A, we have 4 elements, which makes the absolute value of A equal to 4. The cardinality of B is 7, and C also is 7. Now I will move on to finite and infinite sets. Now this is really intuitive and like related to common sense, because obviously if you have infinitely many elements in a set, it's called an infinite set. And otherwise they're called finite sets. And now, even though most of the people know, I will briefly go over through the fundamental sets. So N is representing the set of natural numbers, and W represents the set of whole numbers, though in my upcoming slides, I will flexibly use N as encompassing both the natural numbers and whole numbers. So please just keep that in mind. And Z, as we established before, is a set of integers, including the negatives and the positives. Q is a set of rational numbers, and R is a set of real numbers. So we have all these infinite sets, but the question arises of whether all these sets have the same cardinality. The answer is no. They have completely different. So in order to show this, I will talk about bijections. Basically, a bijection is a function between the elements of 2 sets where each element of one set is paired exactly with one element of the other set. So if we consider a function, as we know, has a corresponding output for every input. And it's the same with bijections, except that we use this in sets. So if there exists a bijection F for A and B, then sets A and B have the same cardinality, and therefore the absolute value of A equals the absolute value of B. And the cardinality of 2 sets have to be equal only if and only if they have a bijection. So if they don't have a bijection, then they by 100% chance don't have the same cardinality. And now we don't really use this for finite sets, because basically all we just need to do is just count them. So if we have set A as 2, 3, 7, 8, we could just count that it has 4 elements. So we don't really need to use like a bijection. But it gets different when we consider infinite sets, because we can't really count the number of elements it has. So I'm going to start introducing a bunch of theorems about comparing the cardinalities of infinite sets. And I'm going to start with comparing the natural numbers and the integers. And as I said before, I will try to encompass 0 in the natural numbers in this case. And keep that in mind. So the theorem presented initially may seem very surprising, because you can intuitively think that Z encompasses both N and the negative integers. So shouldn't Z have like technically twice the cardinality of n. But contrary to what we think, like this, where 0 corresponds to 0, 1 corresponds to 1, and etc., we can actually make a bijection that makes each element of z correspond with each element of n with a 1-to-1 correspondence. So what we need to do is make a piecewise function. And as I established before, functions are basically very similar to bijections in the sense that it has one output corresponding to one input. So what I just need to do is list the set of integers in a particular way in turn that we alternate the positives and the negative integers. So on top, we have the natural numbers, and on top, we have the integers listed in a particular way. And what we just need to do is for the piecewise function, for every n natural number, if it's even, we just need to do negative n over 2. So for example, if we have 8, we make it into negative 4. And if it's odd, we just do n plus 1 over 2. So if it's 9, it becomes 9 plus 1 is 10, divided by 2 is 5. But then, obviously, all sets are not completely equivalent, especially when we're considering the natural numbers and the real numbers. Now, this proof is actually very interesting because it's not really like mathematical, but it uses like very, very unique intuition in order to show this to be true. So if we compare the set of natural numbers and that of the real numbers have a much greater cardinality than the natural numbers. So how do we show that? I first list the natural numbers on the left corner, so from 1 to 14 and so on. And for each natural number, I'm going to write a decimal number with a that is between 0 and 10 exclusive. So it's going to have one digit, a decimal place, and technically infinite number of decimal places, digits following after that first digit. So what I just need to do is prove that there exists some decimal number like 4.4705 that is not included in this set. So what I just need to do is, it's actually a really famous proof. I just need to draw a diagonal line through all of these numbers. So I'm going to highlight the first decimal place of the first number 4, the second of the second one, 0, the third of the third one, 2, 1, 9, 8, and so on. And all I just need to do is, in order to make a number that is completely different from all of these infinite numbers, I'm going to change these numbers and make it into one whole number. So what this means is that I'm going to start by making it 0 point. It doesn't really matter. You can just make it like 1 point, 2 point something. It won't really matter. And I'm going to start by changing this first number of the first element. So it was 4, so I'm going to change it to something else, 6. Now, by doing so, I can guarantee that this decimal number is going to be different from what the first element established over here, because 4 is not equal to 6. And the same corresponds to the second one. I'm going to change the second digit into a different number. So I have 0, I'm going to change it to 1. The third one was 2, I'll change it to 4, and so on. So if I make a diagonal line and make an infinitely stretching number, then I can guarantee that this decimal number is completely different from all the numbers I've written down over here. So therefore, the set R is greater than the set of N, meaning it doesn't have a bijection and they do not have the same cardinality. Now, I'm going to move on to showing visual proof. So the previous theorems I've established were very mathematical. They just used pure numbers, but now I'm going to show that you can use geometry in order to show such a bijection. I have a graph provided, and I'll probably give you guys like, let's say 30 seconds to just think over how you can probably show that this cardinality of set 0 to 1 is equal to the cardinality of the real numbers from 0 to infinity. Yeah, I'll just give you like 30 seconds to briefly think over. So I will show a geometric proof in order to establish a bijection with such two sets. So all you need to do is first you establish a point on the center of the semicircle we see over here. And all we need to do is from that point, we connect one line from that to the real number line. So if we do so, we're going to have multiple infinite straight lines connecting each point on the semicircle to the real number line. And this bijection, one-on-one bijection, shows how the cardinality of the set from 0 to pi is equal to all real numbers. So we've been talking about infinite sets for a lot of times, but we haven't really established a mathematical foundation to which how we can represent these sets. So I'm going to talk about a brief mathematical definition in terms of how we can represent these terms. So first, we can say that a set is countably infinite if it has the same cardinality as the set of natural numbers n. And in mathematical notation, we call this LF naught, and it's written like this. And we have seen before sets like real numbers or 0 to 1, which don't have a cardinality similar to n. These sets are called uncountable infinite sets, and these are written as LF1. Though LF0 and LF1 have completely different cardinalities and they're dealing with a really, really complicated situation of infinity, we can establish a relationship between these two sets by showing that 2 to the power of LF naught is equal to LF1. This shows that we can actually find a more precise way in order to represent the cardinality of sets of real numbers and natural numbers in terms of basic numbers. So we've been looking at multiple fundamental sets, such as the natural numbers, whole numbers, which are basically the same thing, and integers, as we established that they have the same cardinality of natural numbers. And we've also looked at real numbers, which have the cardinality of LF1. But one part we haven't looked at is the set of rational numbers. So one might be curious whether this has the cardinality of either LF0 or LF1. The quick answer to this is that it's LF0. So I have previously mentioned in a mathematical definition that a set is LF0 if it's countably infinite. So you actually don't need to like think it really deep into this. If you can actually just like technically count the number of elements into one set, we could just actually call it as countably infinite. So what I'm going to do is I've currently set a line of integers with contrasting of positive and negative integers starting from 0, 1, -1, 2, -2, 3, -3. And from each number to down, I've started to write down the fractions from starting from that real number as a numerator and put the denominator in terms of its reduced fraction form. So for example, with 1, we have 1 over 1, 1 over 2, 1 over 3, blah, 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 blah. And we have 2, we have 2 over 1, but we skipped 2 over 2 because it's not in its most reduced form. We go to 2 over 3, skip 2 over 4, 2 over 5, and etc. for all those integers. So in order to form a bijection, I just try to form a zigzag line along the whole set of numbers. So we start from 0 over 1, and we continue to have like this squiggly line through all of the numbers we see over here, forming like technically a square, but in a more complicated form. So we start from 0 over 1, 1 over 1, 1 over 2, -1 over 2, -1 over 1, and so forth. By doing this, we can set a bijection and can technically count the number of elements in the set of rational numbers. And therefore, we can easily say that the cardinality of set of rational numbers is equal to LF0. So where have I seen these sort of sets? So I've actually been introduced to this problem since I was in 5th grade. So everyone here would have probably seen the Hilbert's infinite hotel problem, where you have a hotel with an infinite number of rooms, but the manager there says that it's completely full. And the main question it arouses is whether you can fit one more person into the room. And the quick answer is yes. You can just move each person from their room number n to the room number n plus 1, and room number 1 will be full, will not full. So it is the same for countably infinite sets over here. If we, for example, say we have a bus coming to the hotel with a countably infinite number of people, how do we fit all these people into the hotel? So it's a really, really simple proof. As we've shown to the bijection to the set of natural numbers and the set of even natural numbers, we can just move every person from room n to room number 2n, and therefore the room with odd number room numbers will be open for the people in the bus to be filled with. And another really interesting paradox that I've been encountering when I'm doing some research is the Barnard-Tarski paradox. This is probably a bit less famously known than the Hilbert infinite hotel problem. But this basically says that if we have, for example, a empty sphere, we can cut it into a finite number of subsets. And if we apparently reorganize it in some particular way, we can make two identical spheres. Now, this seems extremely paradoxical as we're basically making something out of nothing, but using some complicated infinite set theorems and axioms that is currently really hard to understand for a high school student like me, we can prove this to actually be true. So I brought this up in order to show that like infinity is a very complicated term, and even for mathematicians, they can't really create a very systematic way in order for every one of us to like approach this in a proper way. So I thought this would be really interesting if I can bring up for you guys to just become interested in maybe some of the proofs that arise from these problems. Yep, that's it. Thank you very much for listening.
선생님이 오늘 유천이한테 미리 부탁했던 거 있어요. How did you get your idea and how you collected your idea to show your presentation for the beginners? And please share your experience with us.
So what I actually did was I just tried to recount all of my sort of math related memories, even down to like elementary school. That's like fine. So what I found interesting was, for example, the Hilbert's infinite hotel paradox was, as I explained, a concept that I've been introduced to in like 5th grade. But the term of infinity has been really interesting and really sort of like curious to look deeply into. So therefore, I've just like tried to form like a general theme or like a problem, a really specific one it has to be. So if you try to make like an open school presentation, I really don't recommend if you make it like really broad. Like you're just not going to talk about like geometry or like just number theory in general, because it's going to be like really vague, and you're going to have to like talk through the whole thing without like really like a specific goal. So what I try to do is like focus on a specific problem. Like for mine, as I said, it's the Hilbert's infinite hotel paradox. And you just do a lot of like, you can just do like self-research or apply stuff you learned in school or in classes or wherever you've seen in order to just expand on that problem. So I've been generally talking about like infinity, and I really doubt that like every one of you knew that like the like cardinalities or like rational numbers have the same number of elements as like natural numbers. So I like really recommend you to find something that can be intriguing. It's like not really well known, and also is very specific to the audience.